Great, let's start. Sorry, we're about 2 minutes late today. Apologize for that. All right, so to tell you a little bit about what we'd like to do today, I want to finish off what we were talking about last week, which was, I believe, question 6 of exercise sheet 2. We didn't really have time to finish going through that, so we'll do that quickly. And I think we'll also just say one more brief thing about cardinality. Did anyone see my announcement on Vula? I gave you a little bit extra on the cardinality stuff, so we'll just talk through that quickly. And then otherwise, we need to start talking about sequences, right? That's going to form a really big part of this course. So we're just going to, we've seen the definition of sequences so far, right, in lectures. What day did you get that? Was it last week or this week? Last week, say Thursday around then, Tuesday, okay. Yeah. Yeah, absolutely. So my hope today is that we're going to look at the formal definition of sequences. We're going to look at why that makes sense. We're going to draw some pictures, why that actually does what we want it to do, and then we'll see some kind of simple examples just to really work on the formal definition, because the formal definition is a little bit weird to get into at first, so we need to get comfortable with it. And we'll see some simple examples, and we'll build up the difficulty a little bit, and then hopefully that takes you to where kind of the TUT's going to pick up on around Thursday, Friday. We're going to do some specific sequences examples in the TUT, so I want you to feel good going into that. Does anyone else have anything else we want to talk about? Particular questions or topics? Anything else? No. So sequences, definitely, we're going to focus on that. But let's try to tidy up what we did last week. So just really quickly, last week, so we're going to talk a little bit about cardinality, just really briefly. And we were saying that in order to understand cardinality, we need the concept of a bijective function. And so we said that...
Yes, could you please, if you have time, go over all those onto bijective?
Absolutely. Well, so I'm gonna give you those definitions, and we're gonna look at 2 quick examples. Then I'd say let's carry on with the rest of the stuff, and then we can talk towards the end if we have time. Otherwise, you and I will just talk one-on-one, because we did talk a little bit about it last week, but we can do a little more now, and then definitely you and I can talk if needed. Does anyone else want to see additional examples on that stuff? Okay. All right. So we were saying that sets have the same cardinality if there exists a bijective function between them. So what did we mean by bijective? We were saying we have this idea, bijective function. We were saying it was one-to-one and onto. Let's just write that clearly, and onto. Okay? And what did we mean by one-to-one? We were saying that we're gonna look at f going from A to B, okay? And we're saying that if there exists x1, x2 in A such that f of x1 is equal to f of x2, then x1 equals x2, okay? So this was our definition of one-to-one. We did talk about this last time, but it's always good to write it out again. And we did have an alternative. This is the contrapositive. We were saying that x1 not equal to x2 implies that f of x1 is not equal to f of x2. Okay? So just to be clear, remember contrapositive, when we have a logical statement that says A implies B, so if A is true, then B is true. To get the contrapositive, we have to do, I'll just write it over here. So A implies B, the contrapositive is that B false implies A false, okay? So whenever you see these definitions, if a definition says something like A is true, if A is true, then B is true, the contrapositive is saying if B is false, we start at the end here, if B is false, then A is false. So I just want you to understand that this definition of one-to-one is the contrapositive of this definition is the contrapositive of this definition. They are equivalent, okay? So just to see that, we're saying here, if I can take two things in my domain such that, if I can find two things in here such that f of the one is equal to f of the other, then they have to be equal. The contrapositive of that is I start at the end and I say this is false, so if this is false, then it has to be true that the starting thing is false, and you'll just see that that's kind of what I wrote here, okay? Yeah?
Is the converse true also?
Converse, are you thinking contrapositive here? So there's a little subtlety between converse and contrapositive?
Yes, like for instance, if x1 and x2 are equal, then if...
Oh, I see what you're saying. Yeah, so in general it won't be. Just because in general, we're just going to say something true implies something else true. It might not be the case that this implies this, but this is always equivalent to that. Now in this case, you can ask the question, is it true that x1 equals to x2 implies f of x1 equals f of x2? So let's just ask that quickly, aside. What about x1 equals x2 implies f of x1 equals f of x2? Is that fine? Yes, this is always true. Okay, this is actually built into our definition of functions. We don't go into it too deeply in this course, but if you do a course in set theory, you'll just very carefully check that. And you gotta kind of believe me that this actually makes sense, right? Because we're saying like if you take any two numbers and you put them into this function, you should get the same thing out if those two numbers are the same. Okay, we wouldn't want to say like what is 2 squared and that equals to 3 squared. That would be kind of a problem. So we're going to build it. So this is always true, but it's not really related to this definition. This is just true for any function. Okay, but just to answer your question. Okay. So that was our definition for being one-to-one. So let's just quickly write out what it means to be onto. Okay, one more time. So onto, we are saying that maybe I can. Up here. That's a bit high. Okay. Sorry about that. So for onto, we're saying that, so for all, let's say, B in B, there exists an A in A such that f of A equals to B. Okay? And again, we're just using that f from A to B. And we talked about last time, the intuition between these two definitions is that what onto is telling us is it's kind of telling us that I cover everything in the range. Okay? When I apply stuff to my domain, and I go with my function over to the range, over to B, I don't miss anything. Every point of B is hit by something in some sort of loose language. And let's just see, that really is what this says. It says, for all B in B, in other words, anytime I take some element B of this set, which is the range, I can always find something in the domain so that I can get to that element B by applying F. That's what onto. So I kind of cover the range. That's the idea. What is one-to-one telling us? It's telling us that kind of unique points in the domain map to unique points in the range. You can really see that probably the easiest in this version of the definition. If 2 points are different, then they map to different places. They don't kind of collapse to the same place. Okay, so that's the idea of one-to-one. One thing gets mapped to one thing, another thing gets mapped to another thing. That's the idea. All right, any questions so far? Otherwise, we're going to just go to some examples. Any questions? Sorry, I'm going a little fast because I just want to go through that stuff from last time. All right, so I had a question here that I put on Vula, and we kind of briefly touched on it last time, but we didn't really resolve it. So we asked a question. I claim that maybe I'll write it a little bit bigger. Sorry. So I'll put that up there. I think we'll just use a lot more space for this. Okay. And actually, let's do it this way. We're gonna quickly put our definitions here. So one-to-one, we're going to say x1 not equal to x2 implies f of x1 not equal to f of x2. All right, and we'll put our onto here. For all b in b, there exists an a in a such that f of a equals to b. Okay. So now the thing I asked you to think about on Vula, and it's okay if you didn't have time, but did anyone think about this thing involving the empty sets? Anyone have a chance to think about that? So we'll just write out what I mean. So I claim every function f from the empty set to some other set b is one-to-one. Okay? Anybody have a chance to think about this? So this is a sort of a strange thing to say. No matter what set b I pick here, if I take this empty set, the set that has no elements in it, but we agree we're going to allow in our theory, it's always going to be one-to-one. Okay, why would that be true? Well, one way of thinking about it is, we look over at our definition of one-to-one, I have to say that if I take 2 points in the domain, they have to go to separate points in the range. But there are no points in the domain. Okay? So there's no way for this to be violated. Okay? There's no way that I could find points that make it not true that it's one-to-one. That's one way of thinking about it. Another way is if we looked at that other definition of one-to-one, that contrapositive, the equivalent definition, where we said if f of x1 equals f of x2, then x1 equals to x2. Okay? That was also another way of saying something is one-to-one. Well, we look over here, and we'd say, well, it just has to be true that every time this is true, this is true. That's what it means to be one-to-one. If this is true, I don't know if you can see with this chair. If this is true, so if I can find 2 points so that their image is equal, then it has to be true that those 2 points are equal. Okay? So I go over here, and I say, well, anytime that I find 2 points that are equal, their image in here, the points that they came from in the domain have to be equal. Well, yeah, that's always satisfied because this never happens. Okay, because there are no points in the image. Okay, so this is kind of a subtle point, and it's not really a major component of the course. But it's just that we had a question about the empty set, and we have questions about one-to-one. And I just want you to be able to say, hey, I can look at something a bit weird. Someone shows me this on a test or something. Do I actually know how to apply the definition in this special case that is maybe a little bit unusual compared to some of our other examples? Okay? So whichever one works for you, just try to convince yourself. Something has to be a one-to-one. I have to be able to find 2 different points in the domain that are different, that go to different, or sorry, every point in the domain that is different has to go to different points in the range. That is always true here, because there are no points in the domain that are different. So I can never violate this condition. Okay? Or you can look at this version of the definition, the contrapositive. You can go from here to here with the contrapositive, or you can go from here to here with the contrapositive, and convince yourself that this is true. Are there any questions on that? It's quite a weird thing to talk about. Any questions? Okay, so let's go to the next example. So I claim no function G from well, let's stick with F. So F from the empty set to B is onto, okay? Unless B equals the empty set also, okay? So let's see if we can practice applying our definition, okay? Maybe I'll write this one out a little carefully, so you have something to kind of go back and check. Okay, so proof. So I want to prove that every single function from the empty set to some set B cannot be onto, unless B is also the empty set. Okay? So what do I have to do? I have to show that every time no matter what function this is, and no matter what set this is, unless it's the empty set, every single point in B, there at least has to be some point in B that is not mapped to by some point in A. So just to be clear, maybe I can write that. So onto means for all B in B, there exists an A in here such that f of A equals B. Okay, that's your definition. It's saying for every point in the range, I have to find something in the domain such that this is true. Okay. Now, you can say, well, maybe at this point you can already realize that this can't work. Okay, because we have to say there exists a point in the domain and there are no points in the domain, so it can never be true. Does anyone want more than that? I think perhaps that's even convincing at that stage. You could just write, but there does not exist any A in here, so this is impossible. Okay, that would be completely sufficient. We have a lot of questions in the tutorials. What is sufficient for a proof? So how do we get comfortable with knowing what's sufficient? Do lots of examples and ask your tutors. So this is enough. You might feel like you're not done, but you really are done at this point. Okay. What about this counterexample? I said there was one exception. Sorry, not really a counterexample, but an exception. I said that no functions are onto, unless this is also the empty set. Okay. So we're just going to look over here and say, what about G, just some function G that maps from the empty set to there? Okay. Can you see that in this case, I actually, again, cannot violate the onto condition? We're now sort of in a similar situation as what we said about doing one-to-one, going from here to here. So remember, we need to look at every point in the range and find that there's some point in the domain that maps to those points in the range. That's what our definition of onto says. It says look at every point in the range, and for each point in the range, you have to be able to find something in the domain that maps to that point in the range. But there are no points in the range. Okay? So this cannot be violated. Okay? So this function is actually onto. Okay. So just be careful, that's also a bit subtle. All right, any questions on that? Yeah.
How would you then write that?
Write that carefully, absolutely. Let's write it carefully. Okay, so let's say something like this. I'll show you two ways to write it, I think. I think both will be informative. Okay, so proof. Okay, so we'll say version 1. We'll say proof 1. We'll write two quick proofs. All right. We need to show, we could say like this. Suppose G is not onto. Okay? This means, and it's really useful to practice writing this, what is the contrary of saying that it's onto? What is the opposite of being onto, or what would be the contrary of being onto? Suppose G is not onto. This means that there exists a B in here such that for all A in the domains, this is getting a bit funny because the domain and the range are the same, but I'll just talk through that, such that for all here elements of the domain, f of A is not equal to B. Okay. This is this thing you hear sometimes in the tutorials about seeking a single counterexample.
Wouldn't it be G of A now, or would it be still F?
Excuse me, that's my mistake. Thank you very much. Yeah, we specifically made this G, so yeah, it should be G, absolutely. So this is the thing we're talking about in the tutorials, where we're saying we claim that something is true for every single B. I don't know if people in the back can see. We claim that something is true for every single B, then there exists this A. If we want that to be false, there just has to be a single one that breaks it. We said it was true for if it's true for every B, then it's onto. If there's at least one where it's not true, then it's not onto. So we're going to suppose it's not onto. So there has to be a counterexample. This means that there has to be something in the image where nothing in the domain maps to that point in the image. This is what we're doing. So we got to make this false. So we got to put a not equal here. We've got to turn this into a there exists, and we have to turn this into a for all. That's a general pattern of what you're doing when you're taking the contrary of here. You have to make this not true, and generally a for all will turn into a there exists, and a there exists will turn it into a for all. But make sure that you can translate it into like an actual sort of sensible thing that works for you. Okay. So do we agree that this is what it means to be not onto? Okay, and then maybe now you'll see where I'm going. We have to find something in here such that something else is true, but we can never find that because this is empty. So you might ask, how do I conclude this? How do I conclude this? How do I just finish off this proof? Well, you just write, but has no elements. You could say that, or you could say is empty, has no elements. So this, let's clean this up. So this is impossible. Okay. And then you could just write, then G is onto, if you really want to kind of conclude. If you were writing out a proof, say on a test or an exam, and you just didn't write this last sentence, that would be fine. If we're marking it, we know what you're doing. Don't worry. So you've given us the fact that this is impossible, and we're happy. But it's always nice to kind of just sum it up. You know, if you can do it briefly. All right. So this would be proof by contradiction, right? Okay. Okay. So what if we just proved it directly? of 2, okay? Well, it's going to be very, very sort of similar in idea, although it's not technically a proof by contradiction. We're just going to say, so you could write something like this. The range of G is empty so I mean, honestly, I would actually be happy. Sorry, I just got to think about this for a moment just to make sure that I don't just write exactly what I already wrote again. But so sort of, so I would be happy if you at this point said the range of G is empty, so so it's impossible to violate the onto condition. Like that would actually be like definitely communicate to me what's going on, but I think maybe you want some more practice in writing it out carefully. So I think if you feel that you're being too loose, you could go for this version, but I would definitely be happy with you saying something like, the range of G is empty, so it's impossible to find points in the range that violate the onto condition. Maybe we'll write this, condition of being onto. Condition of G being onto. Okay. So this may seem like more words than we're normally writing in the course, but honestly this really tells the story exactly how it is. If you feel a bit safer, you could use this other version where we just did proof by contradiction. Okay. All right. I'll just let you copy that down for a second. Maybe I can. Let's see how we're doing for time. Okay. So I think I'm going to move on to exercise sheet 2, question 6. I'll write it up here in case someone doesn't have the exercise sheet. But are there any questions on this before I start erasing stuff? This is just a little practice on onto and one-to-one in a slightly more difficult context than we normally look at. Good. Questions? Take pictures. Okay, I'm going to start erasing down here. All right, so it is exercise sheet 2, question 1 for those who have the sheets here, but I'll just write it up quickly. Sorry, no, did I say exercise sheet 2, question 1? I mean exercise sheet 2, question 6. That's the one we're looking at. It's that one involving the infimum and the absolute value. Okay. So one thing we just wanted to talk about quickly before we really go in, I want to convince you that A minus B, where A and B are just any real numbers, doesn't matter if they're negative, doesn't matter if they're pi, doesn't matter anything what they are, they're just real numbers, is the distance, okay? Or you could think of it as the length, or length, on the real line between A and B. Okay, we're going to use this throughout the course. will you need this intuition every single time? Maybe not, but it's really important to know this. So let's just see what I mean by that. So let's just look at any two numbers, small numbers, please. Two numbers. Any number.
1 and 2.
1 and 2, okay. 1 minus 2. Another example. Something in the back. Two numbers. Any two numbers. 0.5 and 4. That's cool. Can I get some negative numbers? Any other things? Negative numbers? 1 negative, 1 positive? Minus 3 and positive 5, maybe. Okay. So let's put that in here. So I'm going to put 5 first on purpose, just to be a little annoying, and minus 3. Well, not annoying, but to illustrate something. But we might be tempted to make this look easier. Okay. So let's draw the picture for what's going on here. Well, what's the answer of this one? So 1 minus 2 is minus 1, then the absolute value just gives me 1. Okay. What's the answer here? So, well, that's going to be minus 3.5. We all agree. And then the answer is just 3.5. Okay. And what is this? This is going to be minus minus, so it's going to be 8, right? Okay. Now let's look at the corresponding picture, okay, for this one. So here's 0, here's 1, here's 2, okay? You can have 3 if you want, minus 1, okay? For this one, we got to draw 1 to 4, okay? So 0, 1, 2, 3, 4, okay? And this one, we need minus 3 to 5, okay? So probably put this up here so you can see a little better. So 0, 1, 2, 3, 4, 5, okay? And then minus 1, minus 2, minus 3. All right. Now, let's look at my claim. I'm telling you that that's the distance, or the length, between two numbers, no matter what I put in there, all right? So let's just draw what the distance is between 1 and 2, all right? So there's 1, okay? There's 2, there's that. Do you notice that it's length 1? Okay? Do you notice that this length is just 1? Okay? You see that? All right, so I claim that it's the distance between 0.5 and 4. So let's put in 0.5. Right there, and there's 4, right? Okay, so let's just draw that length. Okay. So what is this length? 1, 2, sorry, can't count. 1, 2, 3, and then a little half, 3.5. So do we agree that that actually gave me exactly the length? Okay. Now what if I put in negative numbers? All right, so let's put in 5 and minus 3. Okay, so this is weird. Negative numbers always ruin our lives. Do they? Is that true? Not really. We go 1, 2, 3, 4, 5, 6, 7, 8. The length here is 8, even though I had negative numbers in there. Okay. And that'll work with pi. It'll work with minus 10,000. So, maybe you know this already, maybe you don't, but this is very important to notice. Whenever someone writes down this, what they really want you to recognize is they're talking about the distance between A and B. What do you do if you see this? Okay, what do you do then? Do this. Okay, they show you this. You might need to think about it this. Not always, but sometimes. If there's some reason to investigate the distance, just remember, this is telling you about the distance between A and minus B. This absolute value actually serves a very useful purpose. And it helps us think less. Because in this case, if I want to figure out what the distance between like random negative and positive numbers are, there's room for error. It might take me a lot more thinking. All I have to do is just plug it into this formula, and it'll tell me exactly what the distance is without me ever making mistakes. Okay? All right. So why am I saying that? Well, it's relevant to this question. All right, so let's write out what the question is. All right, so they tell us let's define a function d from I guess it was from x to some set a, okay, is equal to the infimum for all the little a's in this set a of x minus a. Okay. All right, so this is kind of a funny looking function. It's actually, it has two inputs. One of the input is a real number. The other input is a set. So that's kind of weird, but turns out it's a function. And just to, in case you're, for your notes, just to make it really clear, x is just some real number. A, I think they told you that a is not empty. Yeah, they did. So let's just put that in there to be careful. So always write that. When it's not empty, it's not equal to the empty set. So A has at least one element in it. All right, so you'll notice this is really telling you something about distances. Okay, it's talking about the distances between x and a, which a, whatever is in this set, which x, whatever one I put in my function. Okay, and then I have to calculate all the distances. All of these distances, and then I have to find the infimum. So I wrote this out on Gula, but did anyone see how I wrote this out on Gula, by the way? So I don't know if it's a waste of time, or I think it'll be useful to rewrite it out. So I said, let's clarify this. So clarify, okay. Take x element of R, define S, which equals to the set of all x minus a, such that the a come from the set A. Okay, so we're going to make this set S. What are the elements of the set S that I'm making? Okay, it's all of the different possible values. For that object. I take some x, you just give it to me, you give me some real number, I plug it in here. Then I figure out all the possible numbers that this can become once I plug in all the different elements of A. Okay? And every single number that this whole object can become, that's what's in my set S. Okay? So we're going to make the set. Then define d of x, a, to equal infimum of s. Okay. So I kind of prefer writing it this way. You kind of break it up into two steps. It's like I got to figure out what this set S is. That's step one, because that's what all these objects can possibly be. Okay. And then I have to calculate the infimum. And this really is a calculational procedure. I have to literally find a bunch of numbers and then find out what's the greatest lower bound for that set. If it even has one. I mean, we also might want to investigate that. Like, does it even have a greatest lower bound? Okay. So that's what we got to do. All right. Okay. So I think I'm going to keep that example there if possible. Where's this eraser? Oh. And we'll just do this quickly. Well, we don't have to do it quickly. We got time. But, okay, so we'll. So we last time we did a quick one where we said they gave us A equals to I think it was just 0, 1, 2. Okay. 0, 1, 3. Excuse me. So I'll write here example. Okay, 0, 1, 3. And they tell us x is equal to 3. Okay? All right, so they just say, just figure it out in this case. They give you, so this is some function. They give you that value and they give you that. And so they say, okay, can we calculate this infimum of the, can we make the set S and can we calculate the infimum? So in this case, S is just equal to, well, I plug in all the values. So I have this where I plug in 3 for x, and then I plug in the first possible value. Then I plug in 3 for x, plug in this next possible value. And then I plug in 3 for x. That's not how you write 3. And then, oops, this is all going on. And then I plug in the last possible value. Okay? So you see what I'm doing, what this says. It says, find all of these objects where you plug in something for x, and then you allow a to go for all of the different possible things that can come from a. Okay? So we said that a has all of these possibilities, and that's what x is. So I just plug in, I just find out what all the possibilities are, right? Okay? So we simplify, what is this equal to? Okay, so it's just 3, 2, and 0. Okay? So that's the set S. Okay. So what's the infimum of this set? Anyone tell me what's the infimum of this? The greatest lower bound. It's 0, right? There's nothing funny about this set. It's just a finite set of some numbers, so we can always find the minimum element, and that minimum element's in the set, so it's equal to the infimum. So we found out that D3, see I'm plugging in 3 for x of A, is equal to infimum of S, which is equal to 0. Okay, so we finished the calculation. Done. Okay, so now we have to do it for a slightly more complicated set. Okay, I might just erase this. So, just draw a line here. Maybe you want to think of this as being example 1. By the way, these examples I'm doing are in the example sheet. So I'm not pulling these. You can definitely find them if you end up losing them. So example 2. 2. Okay. So now they tell us that they want x equals 3, and A is going to be something that has infinitely many elements in it. It's just this open interval from 0 to 1. Okay. So now our first kind of thing that we did is going to be a little bit harder, because the first time we could just plug in all the possibilities directly and get the answer for what S is and then find the infimum. Now there are infinitely many possibilities, so I'm not going to be able to list them out. Okay, but that's fine. We can still do it. We can say exactly what the set S is. Okay, with this new case. I guess I should point up here. We can say what that set S is with this new case, and then we can calculate what its infimum is. Okay, so let's go up here. So first of all, perhaps I should have just drawn you a little picture here. So I'm sorry if I mess up your notes a little bit. I'm just going to draw a little picture. I apologize for that. So just to compare with these pictures, what we did is we looked at, I'm going to draw 0, 1, 2, 3, -1, okay? And we plugged in all these different values, so we put in kind of 0 to and 3 in there, and we put in 3 and 1, so 3 and 1. Maybe I wonder if we have another color, probably not. So this was, I'll just circle it, that was the value for x, so this was x, okay? And we had 3 and 1, so 3 and 1, and then we had 3 and 3, okay? And then we calculated all of these distances. We calculated that, okay? We calculated that, okay? That was where we got 3, that was where we got 2, and then I can't draw 0, but we had a point that gave us 0, okay? So we can do a similar thing here. We can try to look at the picture to help us, because we're definitely going to have to figure out what's going on. So what's going on in this picture, right? So now I have 0, 1, 2, 3, okay? And I've still got x equal to 3, so I'm going to circle it and say that's x, okay? But now I have the set 0 to 1, like this, okay? Okay, so this is A. And now I have to figure out what are all the possible distances, okay? Can anyone tell me? So I'll write it a little bigger. Okay, so what's in my set S? Okay, so S equals all the possible absolute values. So, so we need to look at all the possible distances between 3 and elements of A. And what does that equal? Anyone say? If you just look at this picture. For example, I can ask you a question. Is the number 2.5 inside my set S? It is, yeah. And we can kind of see that, right? So I want to check, like, if I start here, remember I'm checking my distance from 3 to some points in A. I go 1 to 2.5. That is definitely a possible distance between this and some element of A. And we could say what element of A it is. Actually, it's the element 0.5. Yeah. What about the number 5? Is the number 5 in this set? No, it's not. It's way too big. Like, if I go 1, 2, 3, 4, 5 this direction, I'm just nowhere near A. If I go 1, 2, 3, 4, 5 this direction, I'm nowhere near A. Okay? So can we now have, like, a feeling for what could be in the set? Okay, so what's the smallest number that can be in the set? In other words, the shortest distance? 2, exactly. Is the number 2 actually in there? But it's like kind of close, like approximately. So what do? Open bracket. Okay, there are infinitely many elements in the set, so it's literally actually an interval. Okay, what is the biggest number? I think by now you got it, it's 3. Okay, so those are all the possible distances. That's what the value of the set is. So we literally can write down, it's literally this open interval from 2 to 3. Okay? 2 is not in there because 1 is not in A. Okay? And 3 is not in there because 0 is not in A. Okay, we all got that. Okay? So now we can ask the question, and I think you know where I'm going. What is the value of D? Okay, so we got to figure out D of 3 to A, which is equal to the infimum of S. And what is that equal to? What's the greatest lower bound for the set? It's just 2, right? Exactly. You can check for yourself. What if I pick the number slightly bigger than 2? Okay, 2.1, something like that. 2.00001. You can always find something in here that's smaller than that. So it can't be, and conversely, if you look at something any smaller than 2, you won't get, you can find a lower bound that's bigger than any number smaller than 2. So this is truly the greatest lower bound. Okay, so that's how you do that calculation. Now there's some other examples. We're not going to go through all of them. They're really similar to this. I think you can, they just vary a little bit depending on whether you have a square bracket or not. So then you got to worry about, when I drew this picture, should I include this number or not and stuff like that. But just to show you that if you break this up into different pieces, maybe maybe the notation was a little bit unfriendly where it said, calculate the infimum of this, and it wasn't really clear. Just remember whenever you're doing an infimum, and they're talking about sets, maybe write out what the set is, try to simplify what it is, and then actually finding the infimum is not so bad. Okay? All right, so I think we'll do the other parts of this question because they are useful. They're a little bit more abstract, but this was just to see that weएर actually figure out what this function is doing. Because if you just look at this function and try to ask the rest of, answer the rest of the question, it's a little bit difficult. All right, well, they ask you, the next thing they ask you is, now remember that was just an example for A, now we're just going to any x, okay? Any x and any non-empty set A. So just write that down. So y is d of xa greater than or equal to 0 for all real numbers x and for all sets that are not empty. Okay, so we're no longer looking at specific things. We're just saying this function is always greater than or equal to 0, if you can see that. Sorry. Greater than or equal to 0. Okay, and just to remember what this was, this is the infimum of x minus a from all the elements of a. Okay? Why is that always greater than or equal to 0? Can anyone tell me? I see you whispering. No? Yeah? I thought you were saying, I know the answer, I know the answer. Well, so at least for starters, we know that this was positive, right? So there's some kind of feeling that this might be true, but how do we write it down? How do we like really prove it? And what does this infimum thing do? Is that going to mess us up? I mean, it might, right? So let's check that out. Well, I'll just give you we kind of have any questions? Sorry. We kind of have an intuition for why it might be true. Anytime you do this calculation, you do a few examples, you're going to see that all of these objects are positive or 0. And so when you take the infimum of them, it's pretty impossible to get a negative number. But how do we write that? How do we write that in like 2RA style? Or how do we prove that as mathematicians? Well, we could just say something like this. You could say that so let's write this just to get some practice, to see some examples of how to write really careful proofs. Okay. So we could say that notice that S so again, we're just making that same set S. Is, well, wait, notice that, well, we could say only has non-negative elements. Why am I saying non-negative? That's just sort of a common way of saying positive and 0, right? Because stuff in here can be 0. We saw that in the first example. But it doesn't matter what word you use here. Just make sure you capture the idea that they can only be positive or 0. Okay. So non-negative elements. If you want to write this in kind of math speak, you could say that is S equals to, or sorry, S is a subset of 0 to infinity. Okay, that's one way of doing it. There are many ways of describing this idea. As long as you describe it exactly correctly, you will not lose marks. So if you wrote this sentence, this is absolutely correct. If you wrote this is absolutely correct. Both are. The only time you really get into trouble is if you start using words that are kind of vague. If you start saying like, I'm pretty sure it's true that, like that's not going to convince anyone. But either one of these, you might wonder, do I need to use this notation? Do I need to use this sentence? Either one is perfect. I write them both for you so you just see the whole story. Okay, so we're saying that S is a subset of this. We'll just write this a little more clearly. Maybe it's the same. All right. So then you could say, therefore, 0 is a lower bound for S. Okay, right? So that's true if you say it this way, and it's true here. 0 is a lower bound for this, so 0 is a lower bound for any subset of this, okay? You can reason it out that way. You may encounter that in a more abstract scenario. Just saying one more time, 0 is a lower bound for this set, so if you take any subset of that set, 0 is also a lower bound for that. So that's definitely rigorous if you want to argue that way. But I would also be happy if you just say, we know that 0 is a lower bound for the non-negative real numbers. Okay, so then we use our definition of the infimum. So then infimum of S is greater than or equal to 0 by definition of infimum. Of infimum. Or of inf, if you just want to use the shorthand of inf. Okay? And you're done. That's it. So remember our definition of the infimum? We'll just write that really quickly. So this is why we kind of pick these questions, because we memorize all these definitions, we do a bunch of examples. The question is, can we apply it in a slightly more complicated situation and feel confident that we're done? So remember, infimum, we'd say S equals to the infimum of some set capital S means that two things are true. S is less than or equal to X for all X in S. And 2, that's saying that it's a lower bound. And B, less than or equal to X for all X in S, implies that that B is less than or equal to S, greatest lower bound. So you normally see this with more words. Now I'm writing it with just symbols, so you can get some practice on that. So this is just saying it's if S is this being the infimum of S is saying that it's a lower bound, and then it has to be the greatest lower bound. So if I find any other lower bound, that's what this says, then it has to be true that my greatest lower bound is bigger than that other thing. Well, that's just what we're claiming here. I found a lower bound, so the infimum has to be bigger. Okay. But what is this equal to? This is just equal to d of xa. Okay, and that's all we have to show. Okay, so we can actually just use the definition. Okay, and if you want to write an extra sentence at the end and just say like altogether, d of xa is greater than or equal to 0, that's fine. But honestly, you're done at this point. It's completely okay.
If I say negative 1 is a lower bound, then the infimum of S is bigger than negative 1.
Well, yeah. So let's look at what that gives you. So that gives you minus 1 is less than or equal to infimum of S for all S. That's definitely true. However, the question is asking us. Maybe I didn't make it clear when I wrote it, but it's asking us to show that dxa is greater than or equal to 0. Okay, so we're not all the way there. This could still be negative. Just because it's greater than minus 1, it could be sometimes equal to minus 0.5 or something like that. We really want to show that it's actually, so if I draw the number line, I want to show that only this area is what d of xa can be. I need to rule out that. I need to make sure that that doesn't happen. So we want to start with 0. Yeah. There's another question?
Jonathan, will it ever actually be greater than 0?
Yeah, it can be. Actually, that happened in our last example, right? Remember? So the next question is going to address your question as well. But remember, just write it really briefly. In our last example, we found that S was equal to 2, 3, something like that. Yeah. And so we found that infimum of S was equal to 2, right? Yeah. And really a key part of it is like, is 0 actually in the set? Or look, it could also be if you found out that S looked like that, then 0 wouldn't be in the set, but the infimum would be 0. You see? Yeah. So it can happen. Yeah.
So the question was us finding d of xa.
It was asking us to show, sorry, maybe I didn't make that clear. It was asking us to show this. It was saying, prove this. Okay? Sorry about that, if I didn't make that clear. Do I have it here anywhere? No. Yeah. I guess I erased the original question, so I apologize for that. It was asking us to show that any x that we take and any a, as long as a is not empty, that it's greater, that this thing is greater than or equal to 0. Okay, so there's another part to this question. Yeah, sorry.
About the second part, is that as small as
This part. This x.
no.
Oh, small s. This one, yes, sorry. So this is definitely a small s. This is one of the dangers of using notation like this, so I also apologize for that. But yeah, these are, anytime you see this, we're definitely talking about real numbers, you know. Okay, not anytime, but in this definition. In general, in this course, if you see less than or equal, I would like to say, I don't know if you've seen it in lectures that they use some other notation, but it usually means you're comparing two real numbers. There are places where you would use this notation for sets and groups and things like that. I don't know if you're doing any of that, but yeah. So yeah, that was a small s. And really that's just telling us that this number, literally this number, is always has to be bigger than any other bound, which is saying that it's the greatest lower bound, bigger than any other lower bound. Yeah. All right, so let's see the last parts of these questions, and then we'll talk about some sequences. Anything else on this part of the question? Okay. So then they ask us, so part C, maybe I should label it as well. No, I want to erase this. They tell us, prove that if x is in A, right, then d of xa equals to 0. Okay. Okay. All right. So do we have a kind of feeling for what's going on? Remember, this was measuring all the possible distances between some number x and all of the elements of A, and they're saying that what if this x is actually in A? Okay. Can we prove that that always means that it's 0? Does anyone see why that might be true? And I see some promising looks, but maybe no one wants to say it. That's okay. Well, the idea is, remember, S, as I called it, is the set of x minus a, where a is an element of a. Okay, and well, that means that if I'm allowing every possible element of A to go into this object, and x is actually in A, then it means that 0 is an element of S. Okay? Can we see why that would be true? It's like, I'm considering all the possible things that can be in here, and in particular, there's at least one where this x is in there, so I'm going to get 0 in there. Okay? Do we need to write that out carefully? Or, I mean, there's not really anything special to say there. You can just say that, notice that 0 is an element of S. That's okay. If you define S this way, okay? And well, we know, sorry, so they helped you in the last part. We know that d of xa is greater than or equal to 0. Okay? So there's nothing less than 0 in there. And so maybe we can, from last question, okay. And I think at this point, you can just say, look, you could say this in two ways, so I'll say it in words and then I'll write something down. So you could say, I know that 0 is the lower bound for the set S, and I know that 0 is in the set, so it's the minimum element, and so it's equal to the infimum, okay? And then it's equal to dxa, which is what we wanted to show. Did I write that somewhere? Yeah, prove that if x is in A, then dxa is equal to 0. So you could say that. Another way you could say it is you could say that suppose, but you could do proof by contradiction. You could say suppose this number is bigger than 0. Okay, you know it's always greater than or equal to 0. So suppose it's bigger than 0. Well, that means that the infimum of S is greater than 0. But the infimum of S is a lower bound, and we know that 0 is an S, so we get contradiction. Okay, do you want me to write those both out?
Yes, please.
Yeah. So let's get some nice practice writing these out. Okay. So first, 1, and we'll say this is a direct proof. Okay. Well, so we know that. Let me just phrase this very carefully because I know you want to learn from this. So 0 is a lower bound for S. And proved in previous part, or the previous question. But 0 is an element of S, okay? Then this implies that min S equals 0. Well, we could say min S exists and min S equals 0. Then dxa is equal to the infimum A element of A of, of S, which is equal to min S, which equals to 0. Okay?
Sorry, so if 0, okay, if a number is a lower bound and that number is a minimum, then we conclude that that number is an infimum.
Yeah, exactly. I actually.
Does that like?
Yeah.
Okay.
Yeah. So actually, what we get is we don't need so much and. We need if a number is a lower bound, and then we find out it's in the set, then it's the minimum.
Okay.
That's always true. Can we prove that? Like, very quickly? I want you to definitely be convinced by that. I'm not going to erase the question, I don't think. All right. Okay, so I'm going to keep the question. But we should feel confident about that. We've been kind of using it, you know? We've been kind of saying it a lot, but like, do we feel confident about it? Well, let's just check. What is the definition of the minimum, if it exists? Definition of min of some set B. Okay. Well, we're just saying that there exists an element little b in B such that B is less than or equal to X for all X in B. Okay? So there's something in this set that is smaller than all the rest or equal to them. That's literally the definition of the minimum. So what did we found? We found a number that's less than or equal to all of them. Okay? And that's just your lower bound condition. And then we just had to check, is it in the set? And it is in the set, so it's the minimum. Now, we're going to always say, we've been kind of using this sometimes in tutorials, but like really feel confident to prove it, is that the infimum is going to equal the minimum if the minimum exists. Okay? Can we prove that? Well, remember what we got to check for the infimum. We got to check, is it a lower bound? And if there are any other lower bounds, they have to be smaller.
So then how do you prove that part?
Okay.
And then how does the minimum suggest the second part is proved?
Exactly. Okay, let's do that. Good question. So let me just get a little more chalk, because okay. So let's just write that. We'll return back to this. So claim, let's say aside. I claim if min B exists, this implies that min B is equal to the infimum of B. Okay? Okay. So let's prove that. I mean, you may be able to kind of visualize it, but let's prove it carefully. So we need to show. So we need to show one and two. Min B is a lower bound for B. And we need to show that min B is the greatest lower bound. Is the greatest lower bound. Okay. Did everyone copy this down? Did everyone have this? Because I'm going to erase it. I might leave this last line because we'll discuss. So proof, proving one, is min B a lower bound? Well, by definition, and this is really how you would write it out carefully, min B is less than or equal to X for all X in B. And this implies that min B is a lower bound. Okay. Are we happy with that? Literally, so by definition, we're just saying what is min B? It's that element which is less than or equal to everything else in B. And that also happens to be the lower bound condition. What's the difference? Min B has to be in the set. For a lower bound, it doesn't have to be in the set. It could just be much smaller. Okay. And then two, so now we want to just kind of take this away. So now we would need to prove that it's the greatest lower bound. Okay. We could do proof by contradiction, but it's kind of nice to practice all these things. So So we'd say let B, have I used little b? No, good. Actually, let's write it this way. Let C, sorry if I messed up your notes, be a lower bound for this set capital B. Okay. Then C is less than or equal to min B. Okay. Or I can write this carefully, because it's an element of this set. Okay. So what does it mean for something to be a lower bound? It means that it's less than all of the elements in the set, right? Well, min b is in the set, so it has to be less than or equal to min b, by definition of being a lower bound. But remember, if we look back at what we needed to show that min b is the greatest lower bound. And I just showed you that if you take any other lower bound, min b is bigger than it, right? Just by the definition of being the minimum. So we kind of said, like, if you had to kind of draw it on the number line, all of this kind of translates over into a picture that we have in our heads. But this is really how you prove it formally. And the reason why you do this is because we don't know what's going on with this set. This set could be very, very weird. It might not be something that's easy to draw. I mean, we might be concerned that something strange happens, but it doesn't. We just proved it. Is that cool? So we just satisfied the two conditions. We just found some number. Remember, this is just some real number. We found a number that satisfies both conditions of being the greatest lower bound, in other words, the infimum. So we showed that if min b exists, as all of this depended on min b actually existing, if it exists, and and that means that really there is some number in the set that's less than all the other numbers, then min b is actually equal to the infimum of b. You could go through the same proof and prove it for the maximum, right? It might be a useful example, or maybe you wait a few days so you kind of forget, and then like maybe a test is coming up in a few weeks, and then you say, can I prove that if the maximum's exists, then it's equal to the supremum? You just go through the same thing. You say, what's the definition of the supremum? I have to satisfy two conditions. Can I use the definitions to show that both of those are satisfied? Okay, so let's talk about why this actually gave our other claim. So remember, going back, what we wanted to show was, we wanted to show that if x is an element of A, then this number here that we calculate is equal to 0. Okay? And we did this whole long proof, and we basically just showed that if x is an element of A, then 0 was an element of that set S. And since 0 was a lower bound for that set S as well, we proved that in the previous question, then the minimum of S exists, and it's equal to 0. It's a lower bound. We found a number in the set that's less than all the other numbers, so it's the minimum of that set. So that minimum exists, and it's equal to 0, therefore it's equal to the infimum. But that's actually what dxa is. It's just this infimum of S. So that's the whole sort of logical train. Okay, so we're running a little short on time. We've got about 10 minutes. We could finish this question, or we could start sequences for 10 minutes. I think perhaps we should do sequences, but I don't know how everyone feels. Is that cool? There is a last part of this question. It's useful to do. It's part D. So I might write something on Vula about it, but I suggest you try it. And if there are questions, we can do that next week. But I think that'll be quite quick if we had to talk about it. Does anyone need a moment to write a bit more before I erase? It looks like, is anyone still writing? Still writing? Okay, so let's talk sequences. Let's see, I always lose the eraser. There we go. Okay. So you've probably seen this already. Well, I know you've seen it. But let's just quickly recall, what do we mean by a sequence? All right, so what is a sequence? Well, one way of thinking about it, quite abstract, but this may help you at some points, is that it's just a function from the natural numbers to the real numbers. Any function, okay? And sometimes given by a formula, say an equals some f of n, and you could have an example. Well, sorry, this is actually just how you write what a function is, but that's all right. But sometimes given like, you could have 1 over n equals, so let's write it this way, an equals 1 over n. You could have an equals to logarithm of, an plus 1, and so on. You can make up all kinds of stuff. Equals to, make up your own thing. An squared plus 2an plus 1. Okay? So they sometimes give you a function. They sometimes give you recursive definitions, but we're not going to need that right now. Any questions so far?
For the third one.
Yeah.
And the second one.
Yeah. They look kind of nasty.
Yeah.
What's?
Is it not supposed to be lim?
Wow, sorry. I just made up stuff. Yeah, that's very good. I apologize for that. I was thinking about recursive things, and then I wrote out something that was different from what made sense. And the point is, as long as they give you some way of assigning a real number to every single natural number, you have a sequence, okay? So, observations. Did they ever start you off at, I wonder if they ever start you off with at 0. All your sequences start at n equals 1, right? Yeah, okay, cool. Because we have said the natural numbers start at 1. All right, so observations, sequences always begin with kind of A1 equals to something, A2 equals to something, and so on, okay? Sequences are an infinite list. It's really important. It's infinite list of numbers. Okay? That's what we mean by the domain being the natural numbers. There really are an infinite number of these. Sometimes I've had questions in previous years. What if I get to like the end of the sequence? No, we don't get to the end. It's an infinite list. Somebody gives you a finite list, it's not a sequence. Okay? Yeah, exactly. It's not a sequence. So just observe that. And and since it's, let's say, since since a sequence is a function, it's sometimes useful to draw it, sometimes useful to plot it, sometimes useful to plot. Yeah. Okay, so we're going to return to this picture, but you'd have something like this, okay? And what you have on this axis is n, natural numbers n. It starts at 1, 2, 3, and so on. And you can plot the values, right? This is your domain, this is your range, okay? And so, you know, let's say we plot, you know, the sequence f of n, or let's say a(n) equals to 2. So what is that? That's the constant sequence. So that's 1, that's 2. Okay, so I would just put a point there, put a point there. Remember, it's not a line, it's a point, because the domain is these different points. So there really is a visual component sometimes with these. You could plot more complicated stuff like 1 over n. I'm not going to draw a lot of pictures right now. We'll see the pictures more when we do examples. Sorry if I covered that up. All right, so then one of the most important things we talk about, I think I'm going to hopefully just go through this definition, and we'll obviously continue on with it more next time, is to talk about what we mean by a sequence to converge. So we have this definition. Maybe what I'll do is I'll start up here. So we have this definition. Sequence, and sometimes they write it like this, you know, an converges to some a, which is just some real number, is equivalent